Hello everyone, my name is Kamil Riedel and I'm a PhD student at Imperial College London, working on enhancing the robustness of precast concrete systems in collaboration with technological innovation group at Langeroog. So today I will discuss the PBBS DFrame system I'm working on, the importance of structural robustness and its assessment. Then I will show how its connection was developed. Next, I'll move on to experimental testing and numerical modeling, finishing off with the whole DFrame Bay assessment and conclusions. Now I'll give an overview of PBBS products and DFrame system I'm investigating. PBBS are product-based building solutions, which are next generation, pre-engineered and highly optimized structural systems. They're efficiently designed with cement replacement materials that can drastically reduce carbon footprint. The DFrame shown here is a PBBS precast concrete system. It can be easily assembled on site, virtually eliminating any wet trades. It consists of inverted U-planks sitting on top of inverted T-beams that span up to 9 meters. With Halflife joint, they don't require any propping. This, however, is their main source of discontinuity. Providing robustness under structural member loss in PBBS precast systems is the subject of my research. So let's talk about structural robustness. Many of you probably know about Rollman Point. A gas explosion on the upper floors damaged the structural wall, which initiated a progressive collapse. This was an incentive to design buildings against disproportional collapse. There's a building in Kiev hit just 2 weeks ago by missiles. There's a tragic and highly unnecessary conflict. However, it should be appreciated that this building stood up despite a corner column removal, which prevented a collapse, potentially resulting in a high number of casualties, showing the importance of robustness. Currently, the industry prefers the use of convenient prescriptive tying rules, which are acceptable in the current revision of Eurocodes. Conceptually, they are to provide a degree of robustness by tying the structure together. This does not explicitly assess the robustness, nor it guarantees that the structure doesn't collapse. Instead, an ability of the structure to develop alternative load paths should be assessed through a quantifiable method, such as an instantaneous column removal. A realistic assessment can be then done using a pseudostatic approach that can conveniently account for dynamic effects through energy balance methods. It transforms a normal static response that can be easily found in most FE software, shown here in a continuous line, into a pseudostatic response, shown in a dashed line. Its peak indicates the maximum dynamic resistance. For an elastic response, the ratio of static to pseudostatic resistance is 2 and 1 for perfectly plastic response. It is important to differentiate a monolithic response from a precast one. You can see in the graph static and pseudostatic comparison of the DFrame column removal represented in orange curve against an equivalent monolithic section with the same level of reinforcement with a blue curve. A typical monolithic response consists of 5 stages. Initial flexural action, followed by a compressive arching action, and at approximately beam depth, catenary action can be activated. Around the transition to catenary, the bottom reinforcement in the sagging section under the removed column fractures, resulting in immediate softening of the curve. Catenary action allows for substantial static load recovery. But as can be seen in the dashed blue line, it doesn't necessarily offer much extra dynamic resistance. The ultimate failure occurs by the fracture of the top hogging bars around the columns at approximately 0.2 radian cold rotation. Precast connections are normally less strong than the beam they are connected to, and DFrame would not recover after the bottom steel assemblies fail. Due to stress localization, they can fracture before even entering the catenary stage, which was tried to be mitigated in the design. Therefore, our aim was to maximize the response by delaying the fracture of the bottom assemblies. And as you can see here, the peak pseudostatic resistance of the DFrame compares favorably with its monolithic equivalent. So let's discuss how the continuity of the Halflife joint in the DFrame system can be provided. Two Halflife joints connections were developed. The first plated connection was designed to meet the time requirements given in Eurocode. It consists of top and bottom plates that are simply anchored in the beam with 6 M24 bolts and U-bars to tie them up. The initial assessment showed that the low ductility was available, resulting in an early failure, so an alternative connection was proposed. The bracketed connection was designed to maximize its ductility. The beam primary top and bottom 2B40 bars are attached to purpose-designed brackets during the cage assembly, shown here in red. The beams, when positioned, can be connected with bolts and roller bearing washers that provide a degree of rotation between the beams. To further enhance the ductility of the systems, the bonding on each side of the connector was proposed. Next, we wanted to experimentally test this connection to calibrate FE models. As the whole damaged bay would be at least 80 meters long, a portion with a sagging joint was tested instead with full-scale beam section and a 4-point bending test. To provide horizontal restraints, a passive reaction frame was designed. We tested 2 specimens with no debonding and 350 millimeter debonding lengths. As can be seen in the video, the deformations are concentrated by the joint opening, with the rest of the beam remaining relatively rigid. The failure in both beams was caused by localized combined tension and bending of the bottom B40 bar. High displacement failure of the debonded specimen, seen in the graph in orange, was caused by greater elongation of the bar, which can be seen in the with the naked eye in the video. Next, I could go into numerical modeling and calibrating the model. I used a simplified component-based design where the bars were connected to the beam with springs to account for bond slip. The joint was replicated with a series of rigid links, contacts, and beam column elements. As can be seen in the graph, good correspondence was achieved to the experimental tests. I used a similar component-based approach to model the plated connection. I verified the response using 3D model in Abacus, where the plate was modeled using ductile fracture theory. I found that both component-based and solid models give similar results. With all that information, I could finally go on to the DFrame robustness assessment. Using the component-based modeling described earlier, I analyzed the whole damaged bay under the middle column removal. As you can see, the double span consisting of span 2 and span 3 includes 2 joints working in hogging and sagging. I tested a plated connection against bracketed connector with no debonding, 350 millimeter and 650 millimeter debonding length. The failure occurred in all the models in the sagging joint too, due to the fracture of bottom assemblies, as in the tests. The plated connector, despite having higher static strength, shown in blue continuous line, has lower robustness, which is quantified with a pseudostatic resistance shown in dashed line in the graph. All the connector brackets failed at higher displacements, which increases their pseudostatic resistance. The 650 millimeter debonded model offered the highest failure displacement and resistance. So in conclusion, as shown by the plated connector response, adhering to the tying rules doesn't guarantee prevention of a disproportionate collapse, as it doesn't realistically assess its performance under structural member loss. Instead, a deterministic measure such as a pseudostatic approach should be used that accounts for the dynamic effects. It was shown how simple component-based design can be used to assess the effectiveness of precast concrete joints and to ensure they meet the required performance levels. The analysis should also include any potential local impact on the connection assemblies that can cause early failure. These models should be verified ideally through experimental testing or at least through more sophisticated micromodeling. I was very lucky to be a part of a real-life project and that my research findings had an immediate impact on the industry through a logical evolution of the DFrame critical connection. Thank you for your attention.
Thank you, Kamil. Right on time and a fascinating presentation as well, and very topical with the move everywhere to off-site manufacture, modern methods of manufacture, construction, and so on. I wanted to kick off with a question, which is, I wonder if you could tell us more about the other connections that we might need to tie together. So you focus very much on the beam, and you could really see some in-depth, physical models versus numerical, and how does that relate to the other types of tying and connectivity that we need to think about?
Yes, that's an excellent question. So in any analysis, you would assume certain boundary conditions, so certain horizontal stiffness and rotational stiffness. Now, these obviously contribute beneficially to the response of the whole damage system. But if you look at that simplified image I have here, to ensure the transfer of any tying forces, they have to go somewhere. They can potentially be activated through sort of ring action within the undamaged part of the floor. But this, you would have to ensure that you have sufficiently strong connection of the plank floor units to the primary beam. So that's another topic, but you would analyze it essentially in a similar manner as you would for the primary beam. So they are equally important.
And presumably the column connection.
Yes, that's a second thing that I was about to say. So if you assume certain, for instance, rotational restraints here, which obviously positively benefits the whole system, you would have to ensure that you actually you have some moment resistance between the beam and the column, and we came up with a design that has sort of a vertical ties that go through the beam and connects the top and bottom columns.
Thank you, Kamil. So we have a question now from the audience from Nada, who says, great presentation. I have two questions. Number one, did you model the global effects of the connection on the structure? And number two, could you give us any more details about the building in Kiev?
Right. So for the first question, there are different approaches when assessing the robustness of the building. And yes, I also looked at sort of the 3D response of the building with slightly more simplified connections between the beam and the planks. Such analysis is obviously much more demanding and can be just combined through a multi-level approach. So you can have separate 2D analysis of the beam and then separate analysis of, let's say, damaged planks, and you can contribution of the plank ribs, and you can combine them together into that pseudostatic curve, which is a great way of quantification of robustness. So it depends on the designer. As for the building here, I mean, that was very recent. I think we all follow the news, and it's not very good. It's pretty horrible. But I mean, I just saw that building 2 weeks ago, and I just thought of the research, and I was really impressed that the building stood up. I mean, as you can see here, it does look like a concrete building. I mean, it is a concrete building. And you can see that several columns actually were damaged. So you have this cantilevering effect here. Nonetheless, you don't have the effect as happened with the Roman point where the whole corner of the structure collapsed. It would withstood that damage, which is, I think, amazing. And that's the point of ensuring robustness in buildings.
Yes, I echo your comments, Kamil. I think it's interesting. I think there's a challenge with taking sort of the research work and then how does that get applied into often quite standard or smaller buildings, which might not have the resource to be able to do a really kind of detailed progressive collapse type analysis. So I think what's quite key is things like the connection type work, is how you can do the detailed research to then figure out some simpler rules that you can then apply into our sort of widespread building industry. I'm afraid that's all we've got time for in terms of questions. So thank you very much, Kamil. Very, very interesting and informative presentation.